This video focuses on the confidence interval for the population proportion. The confidence interval is one of two inferences that we'll make in the course about population proportions. Recall that an inference is some decision that we make about a population parameter, a population mean or a population proportion based upon sample data. The confidence interval for a population proportion is based on the sampling distribution of the proportion. Recall that if the following two conditions are met, namely you have a random sample of size n drawn from the population and a sufficiently large sample is selected, which again is defined as one that satisfies the inequalities n times p is greater than 10 and n times 1 minus p is greater than 10. If those two conditions are met, then the distribution of sample proportions has a mean, which is equal to the population proportion, has a standard deviation equaling to this expression below, and is approximately normal. So in other words, we have a normal distribution. Okay, so if we have a normal distribution, we can determine how many standard deviations we need to go up and down from the mean to capture a certain percentage of the data. If we go up 1.96 standard deviations and down 1.96 standard deviations, we'll capture 95% of the data. If we go up 2.576 standard deviations and down 2.576 standard deviations, we'll capture 99% of the data. In general, if we go up z sub c standard deviations and go down z sub c standard deviations, we're going to capture c% of the data. Notice that z sub c depends on what you set as your confidence of your percentage. If it's 95%, then this is 1.96. For 99%, 2.576. For 90%, it's 1.645, and so on. Okay, let's put those two facts together. If we know we have a sampling distribution of a proportion that's normal, in other words, if it meets the validity conditions, then we are C% confident that the sample proportion is within z sub c standard deviations of the population proportion. So if we go up z sub c standard deviations and down z sub c standard deviations, we're going to capture, we have a C% chance that the sample proportion is in that interval. Similarly, we are C% confident that the population proportion is within z sub c standard deviations of the sample proportion. Together, 1 and 2 are really like the old analogy. If I am 6 feet from you, then you are 6 feet from me. If there's a 95% chance that the sample proportion is so many standard deviations from the population proportion, then there's also a 95% chance that the population proportion is within that same number of standard deviations of the sample proportion. This is the key. So from fact 2, we can say that we are C% confident that the population proportion is within this following interval. Start at the sample proportion and go down z sub c, some number of standard deviations, to the sample proportion plus that same number of standard deviations. One small modification we need to make. We're trying to estimate the population proportion. In other words, it's unknown. So in the validity and standard deviation calculations, what we're going to do is substitute the best estimate for the population proportion, which is the sample proportion. So notice in this formula for the standard deviation, I used p hat, the sample proportion, rather than the population proportion, because the population proportion is unknown and I do know the sample proportion. Likewise, in the validity calculations, notice that you have to have a random sample of size n. That doesn't change, but n times p hat, not p, but n times p hat is greater than 10, and n times 1 minus p hat is also greater than 10. Okay, let's use that information for an example. A polling organization is seeking to estimate the proportion of all likely voters that intend to vote for issue 5 during the coming election. As a pre-poll pilot, the organization randomly selects 168 likely voters and finds that 86 of these voters intend to vote for issue 5. Based upon the pre-poll pilot, let's estimate the proportion of all likely voters that intend to vote for issue 5. Use 95% confidence. Since 86 of the 168 voters in the pre-poll intend to vote for the issue, p hat, which is the sample proportion, is 86 divided by 168, or 0.512, 51.2%. Since we're using 95% confidence, meaning we want to capture 95% of the data, we'll need to go up 1.96 standard deviations and down 1.96 standard deviations. So the appropriate calculations are p hat minus 1.96 standard deviations, which equals 0.436, 43.6%, and p hat plus 1.96 standard deviations. And when you do that calculation, you get 0.588. Now, it's very easy using StatCrunch to check your work. Using StatCrunch, if I go to Stat, and we're doing a proportion with one sample. Now, we don't have the responses of all 168 individuals in the sample, but we have a summary of how many said they'd vote for issue 5. So we're going to use one sample with summary. The number of successes, oh, excuse me, my dog is pretty excited about that. We've got 86 successes. 86 individuals said they would vote for issue 5 out of 168 individuals. We want to conduct a confidence interval at a 95% confidence level. And we can then, compute that. And notice what we have. We have proportion, 86% voted for out of 168. The upper limit and lower limits, 43.6% to 58.7%. (43.6) to 58.8. So you can easily check your work with StatCrunch. Now, the second task I'm going to ask you to do is to interpret the interval. An interpretation of a confidence interval consists of 3 parts. Number 1, what is the confidence level? Number 2, what is the parameter that you're trying to estimate? Describe it in terms of the problem. And 3, what are the calculated limits? So from part 1, we know that between 43.6% and 58.8% of somethings. Well, let's interpret that. What we're trying to estimate is the proportion of all likely voters that will vote for issue 5. So we can say that we are 95% confidence level, that the proportion of all likely voters that will vote for issue 5, which is the proportion in the population, that's the parameter we're trying to estimate, is between 43.6% and 58.8%. So that's an interpretation of your interval. That's what it means. From the results from part 2, in other words, from the confidence interval, can you conclude that issue 5 will be passed by voters on election day? So from part 2, we're 95% confident that the proportion of all likely voters that will vote for issue 5 is between 43.6% and 58.8%. So notice something about this interval. It's possible that the proportion of all voters that will vote for issue 5 is less than 50%. It could be 44% or 46%. That's within this interval. It's also possible that the proportion of voters that will vote for issue 5 is greater than 50%. In other words, 55%, 56%. That's also within this interval. All we can say from the interval is that we're fairly confident that the proportion of all voters that will vote for the issue is between 43.6 and 58.8. So we cannot conclusively say that the proportion of voters, of all voters that will vote for the issue, is greater than 50%. So we cannot conclude that issue 5 will pass based on the data in this sample. Finally, are the results, are the processes used in this problem valid? Basically, this question is really asking, is the sampling distribution normal? Okay, for the validity condition, first of all, we have to have a random sample of likely voters, which was given. N times p hat. Notice we use p hat because we don't know what p is. That's 168 times 0.512 is 86.016. That's bigger than 10. N times 1 minus p hat, which is 168 times 1 minus 0.512 is 81.984, is also bigger than 10. So the sampling distribution of the proportion is normal, which means that the procedure, the confidence interval procedure, is valid.